Good morning, good afternoon, and good evening, everyone. So, today we're going to be continuing our linear algebra series, and we're going to start talking about this idea of linear transformations. So, in this section, we consider an important class of functions called linear transformations. And these functions arise in many fields and can be defined naturally in terms of matrix multiplication. So, here's a following example that gives a sense of how one might encounter linear transformations. So say we have an electronics company. So here I'm giving a scenario, and this electronic company makes two different types of smartphones. Okay, makes two different types of phones. Mainly the J8 and the J8 Plus. So those are the two different kinds of phones that they're making. Now the manufacturing, so the things needed to make the phones, the cost of all of that includes a couple of things. So it includes labor, the one who's making it, materials, that's self-explanatory, the things we use to make the things we use to make the phones, and overhead. So these are the facilities that were used while making the phones. Okay. Now, the company's costs in dollars per unit for each type. So here's a brief summary of the manufacturing costs. So someone apparently already recorded this data. So now we know what the costs are for labor, materials, and overhead for both the J8 and the J8 Plus phone that they're making. And we can actually organize these into two vectors, right? We could do that. J8 Plus. This is 73, 101, 34. Now, to determine costs for different manufacturing levels, then we just compute linear combinations of these vectors. So say if we want to produce, for instance, right? If we want to produce 12 J8s and 19 J8 plus, then we just do a linear combination of these two vectors. Pretty self-explanatory. 23, 29. Oh shoot. 93, 29. You add that to 19, 73, 101, 34. And this would give us a resulting vector of 2071, 035, and 994, which tells us that to make 12 J8s and 19 J8 pluses, we would need $2,071 for labor to make 12 J8s and 19 J8 plus. We need $2,071 of labor We also need $3,035 of, I think this was materials, and $994 overhead. Right? Okay. More generally, so here's a more general idea. If we let our x vector be x sub 1, x sub 2, right? These are the indicated desired production levels for J8s and J8 pluses respectively. So I'm just going to say that. So x sub 1, x sub 2 are desired production levels of J8s and J8 pluses. Okay. Here's the thing now, the one we're actually going to talk about. We let t be a function that takes the production vector x, that takes x as input, and produces the corresponding cost vector, and produces cost vector, the cost of everything basically, as output. So using individual cost vectors, we can actually make a function out of it. We say that t is a function of a vector x. It's just saying, it's just the same thing as this vector equation. So x sub 1 plus j8, j8 vector, x sub 2 times, why did I say plus, times j8 plus vector, 34. Right, so we're just writing it in a more compacted way. Okay. Okay, now we're gonna connect some of the stuff we learned from the previous video. Now suppose we have a matrix A, it's 3 by 2. So that means 3 rows and 2 columns. And we're saying it's literally the J8 vector and the J8 plus vector. So that's going to be 57, 93, 29, 73, 101, 34. So we know this is a 3 by 2. That's 3 rows, 2 columns. What we're saying here, so we can write compactly in a compact way. We say our function t that takes in a vector is actually just this guy, the matrix A, and we can multiply it by some vector. And we just say this is AX, right? Oh no, I messed up. Whoops. There we go. Number of columns have to be equal to number of rows in this case. And now let's go back to the example. So to translate everything I just said, so this thing, right? Let's say I want 10 J8s. Say I want 10 J8s and 35 J8 pluses. So we would have this vector here that corresponds to J8 and J8 pluses. And this is just the matrix 73, 101. And here we would get, or no, in this case, we plug in 10 and 35 here, and we would get some value. So we get 3125, 4465, 1480. So that's the cost vector. That's how much labor you need in dollars, materials, and overhead. Oh, overhead. Great, fun stuff. Now let's actually go into the topic of linear transformations. So we actually kind of did it already, but we're just going to formalize it here. Okay. So that smartphone cost function is an example of an important class of functions called linear transformations. So here we let t be a function. So we start at m dimensions and we change it to n. Now I'm going to explain what this is in a bit, but I'm just going to put it out there that here we started with an r by 2. And then somehow we ended up with an r by 3 here, right? Just pointing it out. We're changing dimensions as we're doing a linear transformation. Okay, let's go into some jargon here. We have domain, we have codomain, image, and range. So what do each of these mean? So T has, here's the domain. The domain is the first thing, Rm. So in this case, the domain of our example here is R2. So basically, we're calling it the input vectors. And of course, the codomain is just the output vectors. Rn, which I'll call the output vectors. Could be more. Right. Now, for every vector, say u in Rm, our new vector, so right, this thing here, when we transform it, we're still getting a vector. So this new vector here is basically what we call the image of u under T. Okay. So a lot of info here. The set of all images of U, the set of all of those in Rm under T is what we call the range. Range of T. So there's a mathematical way to write it. Range T. Okay. We're going over this bit by bit. Now we're saying the range of T is a subset of codomain of T. How do we know? Well, if we have this codomain, say in this example, this is our domain. Codomain is Rn. Rn here in this case R3. So the range of T is a set of all images of U in Rm under T. So we're saying this one, right? Yeah. So this is actually just a subset of the codomain. I don't know. We'll see. We'll see what all of these mean in a bit. Okay, I saw the definition here. So we say a function T that goes from Rm to Rn is a linear transformation for all vectors U and V in Rm and all scalars say R we have. So we have to satisfy two conditions in order to say this is a linear transformation. When we add these two vectors and then we transform them, it should be the same as transforming each vector first and then adding them. So that's one property we have to fulfill, or it has to meet. Another property is we scale the vector first and then transform it, which should be the same as scaling the transformed vector. Right? Hope that makes sense. Here's my, I don't see it. Oh, I'm looking at the wrong thing. Okay. Do an example. Here we let t with this vector here be equal to this thing here. So this actually already in the form ax plus 5x sub 2. And that's the function. Our goal is to find t to -1. And we want to show t is a linear transformation. So let's actually complete that first step, right? Let's find t with that vector. So what that's gonna look like is 2, -1. We're just gonna replace 2 to x sub 1 and -1 to x sub 2. Right? And this would give us a vector of 6 plus 1, 7. 4 minus 5, -1. So what does that tell us? This tells us that t started from R2, ended at R2. This is the domain. This is the codomain. What's the image? This vector here is the image of u under t. So it's part of the range of t. What else can I say? Oh, this one. This is the range. Range of all values. Or in this case, actually, this is an image of vector under t. And then we say this is a subset. This is part of the codomain. No, this is the actual value. This here is part of this codomain, right? We say the range is a subset of the codomain. Anyway, I'm just trying to see things out here. That's what we see, right? Now to show they're a linear transformation, or I meant t, we have to get two vectors here. So we let u be u sub 1, u sub 2, and v sub 1, v sub 2. So based on the definition, we want to fulfill both of these, a and b. So let's try it out, yeah? So this is t u v, which is the same thing as u sub 1, v sub 1, u sub 2, v sub 2. And if we plug them into here, this is 3 of u sub 1 plus v sub 1 minus 2 of u sub 2 plus v sub 2. Right? So we're just plugging in stuff. Okay? Oh shoot, this is not 2. There we go. 3, and then 2x sub 1 plus 5x sub 2. So 2, our x sub 1 here is u1, v1. 2x sub 1, then plus 5 of our second component. And then if we expand this, we're going to get something like 3u sub 1 plus 3v sub 1 minus u sub 2 plus v sub 2. 2u sub 1 plus 2v sub 1 plus 5u sub 2 plus 5v sub 2. And then we could separate these out. We could say 3u sub 1 plus, or in this case, minus. Separate the u's from the v's. Minus u sub 2. 2u sub 1 plus 5u sub 2. We add that to 3v sub 1 plus v sub 2. 2v sub 1 plus 5v sub 2. And we can actually translate these into t u sub 2, or 3u, tu plus dv. So we say these are equal, so check, right? Okay, let's try B, the other case. So we want to say that when we scale, it's the same as when we scale the vector and transform it, it should be the same as scaling the transformed vector. So how do we do it? Well, we do this. U sub 1, U sub 2. Here we get R, U sub 1, R, U sub 2. And then we plug it into the function. So 3 R U sub 1 minus R U sub 2, 2R U sub 1 plus 5R U sub 2, right? And then we can cancel out that R. So R is 3 U sub 1 minus U sub 2, 2U sub 1 plus 5U sub 2, right? And this is actually the same as the transformed vector multiplied by scalar. So this is true. Hence, this thing is a linear transformation. Okay? I hope that makes sense. Cool. Okay. Now this next example shows that not all functions, put out there, but here's the catch. So here we're saying not all functions are linear transformations. And here's an example of that. Okay, do example 2. Here you want to show that this transformation R3 to R2, and we actually have a function here. So it's defined by this thing. E of x sub 1 to 3 is equal to x sub 1 minus 3x sub 2 as our first component, x sub 2 multiplied by x sub 3 squared. Now, this is not a linear transformation. And we can check this. We could try doing the definition, see if it works, right? We could try doing that. So let's actually try to do that. I'm going to go with the other definition here, just because it's easier. I'm going to try to prove that this thing is not equal to this thing. Okay, let's try. So here we have this. R u sub 1, u sub 2, u sub 3. And then we plug it in. So we do r u sub 1 minus 3r u sub 2, r u sub 2, r x. Oh, r u sub 3, but we square that. Okay. What is this going to look like? I could factor out the r here. Let me just do it real quick. Here, the r squared u3 squared. If I factor this thing out, why did I put 3 there? That's so weird. U sub 1. If I factor out an r here, I would get u2 r squared. So it's not the same, right? We can see it. This thing is not the same as this, so not linear transformation. Okay. Another way we could have done it was to actually put numbers. Didn't put numbers, but we could do it. Okay. Also, here's a new one. We can combine the two definitions. So that would be T RU plus T SV is equal to R T U plus S T V. It's a fun way we can do it. For all vectors U and V and scalars R and S. Now, the proof here is pretty much equivalent to the first one. Okay, let's try this. We have a couple more. And actually, we should be fine. Okay, I'm gonna say this isn't that hard. Okay, let's try. Right, let's do example 3. So here we let A be 4, -2, 0, -1, 2, 3. And then we let our u vector be -1, -3. Then we have this v vector and 5. Okay. Here we let r be equal to 2 and s be equal to -1 and t of x be ax. Does that make sense? Verify that one holds in this case by separating. Hmm, okay, here's what's asking. The way they phrased it was confusing. We want to solve for this and this. So the idea is we're checking if they're equal, right? Okay, let's actually try it. So start with this thing. This is the same as saying R is 2, right? Multiplied by U. U here is negative 1, 3, negative 1, and negative 3. We add it to S V. S is negative 1. So actually, this should be minus. Minus V, which is 2, 5. And then that's just going to be negative 2, negative 6, minus 2, 5. This is minus 4, minus 11. Okay? Now, oh yeah, let's see. Let's see if that's equal. Let's try to compute for R to U plus S to V. So R is 2 times D of negative 1, negative 3, right? Then we add that to S, or in this case minus. Transform 2 and 5. Are those two equal? Hmm. All right, we use that A matrix. I forgot. Whoops. We're gonna keep this going. So we say this is equal to AX, right? So when we transform, so this is A of this guy right here. That's just matrix vector multiplication. So 4, negative 2, 0, negative 1, 2, and 3. And this works, right? So this is negative 5, negative 14, and negative 33. That's the vector. Here we get this thing. Now, is this equal? So 2 times this matrix and this guy minus this matrix and this guy. Okay, a lot of stuff going on here. So 2 of this thing minus this thing again. I think this was, let's put this down here. Too much stuff. 2, 5. And if we do all of that amazing stuff, we're gonna get the same thing. So we know that this is a linear transformation because they produce the same vector. Or no, not yet. We're not sure. Or actually, we're sure. We're sure. 'Cause we did those two combined, right? So we say that D RU SB is equal to R DU S DV. So it's a linear transformation. Cool. Okay, let's plot some buzzwords here. Specifically, matrix dimensions and this idea of a square matrix. So what in the world are those two things, right? So suppose A is a matrix of n rows and m columns. Hmm. So the dimensions basically n rows, m columns, right? Here's the square matrix. This will only be square matrix if n is equal to m. So n by n. In other words, same number of rows and columns, right? Cool. Guess what the theorem here? 3.2. So here we let A be an n by m matrix. And then we define when we transform a vector, which is literally the same as multiplying a matrix by a vector, then T m to n, we call this a linear transformation, right? Okay, let's do an example here. Before I do, I'm going to copy paste. I'm just skimming through the proof, but it's not really that much of a useful proof because you already have the tools, you know? We have the tools for doing it, basically. So it's not too much of a hassle in this case. Oh, I thought I thought I was gone. Okay, where am I? Oh, I'm here. Okay. Let's see. Right, let's do an example here. So here we let A be a 2 by 3 matrix. 1, 3, negative 2, 0, 4, negative 5. Then we have a W vector, which is 3, 4. Now suppose we have a linear transformation here, T that goes from R3 to R2. And here we know that transforming it is the same as multiplying a vector with it. So we want to determine if W is in range of T. How do we do that? Well, we're not given the function. We're just given a vector and this guy. So when we say a W, that's the same as transforming it. But I think in this case, it's not possible because the number of columns here is not equal. Not possible since here we see that A is a 2 by 3 while W is a 2. So the number of columns of A do not work if my idea is correct. Oh, never mind. We have to do AX. Okay. It's in range of T. I see what's happening. Never mind. I was going to say something different. So I had to make a new variable. So we want T of X is equal to W. So AX equals W. So that is this vector here, 1, 3, negative 2, 0, 4, negative 5 times 3 things, which is equal to some W 3, 4. Right? So we start from R3, and then we get this guy. Okay? So we have to solve this, basically. We can do Gaussian elimination. Let's do that, actually. And this will lead us to this one, which is already in echelon form in this case. This is negative. Okay. And we could leave out the row operations, but this will give us a general solution. This would give me or third. So I'm immediately writing it in vector equation form. S sub 1, or actually in this case it's just S. Because we only have one free variable. 5 thirds, 17, 6, 1. where S is any real number. Thus, W is the image of infinitely many different vectors. Thus, W is the image of infinite vectors. And is in range of T. Okay. All right, we have a couple more, but I won't say we're close, but we're getting there. Let's see. Okay, after this theorem, I'm going to take a break. But by then, we should be good to go. So here we let A be A sub 1 all the way to A sub m. So these are a column of vectors, right? And this is an n by m matrix, n by m, n rows, m columns. We also let T transform from m to n using this idea where transforming it is the same as matvec or matrix vector multiplication. And we say this is a linear transformation from a theorem. I forgot which theorem it was, but I know it was a theorem. Here are the conditions. So vector W is in range of T if and only if AX equals W is consistent. So it has to have at least one solution. What else? Range of T. Oh, this one's interesting. Now we're going back to this idea of spans. The range of T is actually the span of these vectors, which I never knew. Okay, hopefully there must be some way to connect this, but we're gonna do it later. I'll take a short break. Let me just copy this to here. Cool. Okay, so that's all for this video. I hope you guys enjoyed, and I hope you guys learned something, and I'll see you all in the next one.